Hi folks, today we're going to learn about graphing linear equations in standard form. Standard form looks like this: ax plus by equals c. So if you ever see that format where x is not raised to any particular power, y is not raised to any particular power, then that will represent a linear equation. It's important to realize that either a or b can be zero. They can't both be zero, but one or the other can be zero, and you still have a linear equation. When one of those constants is zero, then you end up with a special case. You either have a horizontal line or a vertical line. In a horizontal line, that's when the a value is zero, and therefore your x disappears and only y is in the equation, so you have the form y equals b. And similarly, if you have b equals 0, the y term disappears from the equation, and you're left with something in the form x equals a, and that creates a vertical line. It's important to remember that a vertical line is not a function. It fails the vertical line test. So it's not a function, but it is still a linear equation. It creates a straight line. So let's look at some examples of equations in standard form, and let's start with those special examples first. So y equals 4. In this case, y is constant. X doesn't matter. The y value is always the same no matter what. So what this looks like is we can draw in our axes here, and we go up to, let's see, this is positive 5, this is negative 5, this is negative 5, this is positive 5, and we would end up with y is 4 no matter what. So I would draw a line across here representing my y equals 4. This horizontal line is a function. It passes the vertical line test. You can just hold a vertical pencil or other line against the graph, and you never intersect the graph more than once. On the other hand, when we have an equation in the form x equals negative 2, that means x is constant no matter what the value of y is. So again, if I just use the same markings on my axes here, this is positive 5, this is negative 5, then here, according to this graph, x is always negative 2 no matter what happens with y. So this is my value, this is my graph of x equals negative 2. Notice it is not a function. It fails the vertical line test because when I get to x equals number 2, I intersect the graph more than once. In fact, I intersect the graph infinite times. So those are special cases of linear equations in standard form. Let's do some equations in the more traditional standard form where neither a nor b is 0. If you're given an equation like this one, 3x plus 4y equals 12, is in standard form. We have some number times x plus some number times y equals some constant. And we can graph this equation basically by just figuring out what the x-intercept is and what the y-intercept is, and then 2 points determine a line. So as soon as you have those 2 points, you can draw a straight line between them, and you're all set. So how do you figure out what the x-intercept is? Well, remember the x-intercept is when y equals 0. So if we plug 0 in for y and see what we're left with in the equation, we get 3x plus 4 times 0 equals 12. Well, this 4 times 0 disappears because 4 times 0 is 0. So we are left with 3x equals 12. And we, by dividing both sides by 3, we get that x equals 4. So this tells us when y equals 0, x equals 4. So I know that the point 4, 0 is somewhere on the graph. We can do the reverse for finding the y-intercept. The y-intercept is when x equals 0. So I I plug in 0 for x, so I have 3 times 0 plus 4y equals 12. This portion of the equation disappears because 3 times 0 is 0, and 0 plus 4y doesn't do anything to the 4y. And then I can divide both sides of the equation by 4, and I get that y equals 3. So I know when x equals 0, y equals 3. So I know that the point 0, 3 is on the graph. So now I can plan my graph. All of my points are in the kind of positive region. There's no reason I couldn't plot a negative number if I wanted to, but I'm going to go ahead and make my axes a little bit lopsided because all of my data points are in the positive zone. So I'm going to have, let's see, so this is -2, -2, and I go up here 1, 2, 3, 4, 5. This is +5. This is +5. And that'll help me plot my points a bit better. And now I can plot a point at 4, 0 and at 0, 3. And I can draw a line, a straight line between those points, which I will do my best to do freehand here, but computers, okay, imagine that that's a straight line. Okay. So by plotting 2 points, that's enough to draw a straight line between them. Ideally with the ruler, not something I can do in this situation. Again, in this equation, we have, is written in standard form. I have some number times x plus some number times y equals 6. There's no additional addition or subtraction in there except for the x component and the y component. So let's figure out the x-intercept. Remember, the x-intercept is when y equals 0, so I plug 0 in for y. I get 3/4 x plus 2 times 0 equals 6. This term disappears. I can now, to get x all by itself on one side of the equation, divide both sides by 3/4. Divide both sides by 3/4. Okay, of course, when you divide by 3/4, that's the same as multiplying by 4/3. When you do that, you get that x equals 8. 6 divided by 3/4 is 8, and this 3/4 cancels out on the left side. And so now we have the point 8, 0 as a point on our. For the y-intercept, that's when x equals 0. So I plug 0 in for x. 3/4 times plus 2y equals 6. This component of the equation disappears because adding 0 to 2y does nothing to the 2y. Divide both sides by 2 to get the y all by itself, and I get y equals 3. And now I have an x value of 0 and a y value of 3, and that is a point on my graph. Once again, in terms of plotting this graph, the axes are, all my values are positive, so I want to kind of have more space here in the positive x and y regions of the graph. So I'll just mark the same values here, -2, and go up to +5 and +5 here. And I can plot a point at 8, 0 is up here, and 0, 3 is right here. Once again, if I try to draw a straight line between those, so close. Again, with a ruler on your own, if you can. But 2 points determine a line, and you can draw a straight line between those 2 points. Let's look at another example, this time a real-world example. So, you want to rent exactly enough seating for 180 people. Small tables seat 6 people, large tables seat 10 people. This equation, 6x plus 10y equals 180, models this particular situation. And in fact, so first of all, notice this is standard form. Something times x plus something times y equals a constant. Notice that standard form works well for writing linear equations when word problems have two items with different rates and you know the total. What I mean by that is I have a rate for small tables, which I'm going to call, and that's small table seats 6 people. 6 people per table is my rate. 6 is my rate, it's people per table. Large tables seat 10 people. So I have a different rate for large tables. Large tables seat 10 people per table. That's the rate for a large table. And so I'm combining those two types of rates together to get a known total. In this case, my known total is 180. So here's my story problem. I have an equation and it says graph the equation and interpret the intercepts. So I have the x-intercept, calculate that first by setting y equal to 0. And when I have y equals 0 and I plug it in, that gives me 10 times 0 equals 180. This component of the equation disappears and I'm left with 6x equals 180. So if I divide both sides of the equation by 6, I get, let's see, I'm doing 6x divided by 6 and I'm doing 180 divided by 6. So the 6 disappears and I'm left with x equals 30. I now have x equals 30, y equals 0. So that gives me the point 30, 0, which is going to be one of the points on my graph. Now to do the y-intercept, the y-intercept is when x equals 0. So I'm going to plug in 0 for x. 6 times 0 plus 10 times y equals 180. This portion of my equation disappears. I'm left with 10y equals 180. So I'll divide both sides by 10, and that gives me y equals 18. So when x equals 0, y equals 18. So that's going to be one of the points on my graph as well. Given that information, I now have enough to draw a graph because I only need 2 data points to draw my graph. Before I do, though, I'm also the meaning of these intercepts. So y represents large tables. So when y equals 0, I have no large tables. I only have small tables. So the x-intercept tells me the number of small tables, when there are no large tables, if no large tables. On the other hand, the y-intercept is when x equals 0. When x equals 0, that means I have no small tables. So the y-intercept tells me the number of large tables I have if there are no small tables. If no small tables. So now I understand the meaning of those intercepts. I just need to actually plot the points now. And so I can, it doesn't make sense to have a negative number of tables in this problem. You can't have a negative number of tables. So I'm just going to draw my axes here so that I only have positive values of x and positive values of y. And if I start with 0 here, remember the x is the number of small tables. So I've got small tables on this axis, and I have large tables on this axis, on the y-axis. And I need to get all the way up to 28, 30. So I'm going to count by 2s. Let's see, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So that gets me far enough in the x direction. Let's look at the y direction now. I need to get up to 18 in the y direction. And again, if I just count by 2s, I should get there. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Gets me far enough in the y direction. So if I plot my two data points, 30 and 0, that's right here, and 0 with 18, that's right here. That gives me the 2 points I need to try to draw a straight line between the two. To help me out a little bit, I'm going to put in a couple more data points. There should be a point at 10 and 12. 10 and 12. There should also be a point at 20 and 6. Hopefully that'll help me draw a slightly better line. Okay, well, I've done worse. Okay. All right. So I've plotted the points and I've drawn a straight line between them. There is one more part to this question, and that's finding 3 possible solutions in the context of the problem. So any point on this line is a solution to the equation. But the only answers that make sense, remember this story problem is about tables. You can't have half of a table. And so in the context of this problem, the only true solutions are solutions that are whole numbers. Only whole numbers make sense for both x and for y. And so in terms of the problem, 3 possible solutions. We actually already know 2 of the possible solutions. Those were our intercepts. Those had whole numbers. So I have a point at 30 and 0. I have a point at 0 and 18. Scroll down a little bit. 0 and 18. And so we can have 30 small tables and 0 large, or we can have 0 small and 18 large. But this is asking me to find 3 possible solutions. I know I only have 2 so far. So what else can I do? One strategy here, I mean, you can guess and check. You can, if you've drawn an excellent line, you might be able to see where the points intersect the kind of hash marks on the graph to find out where the whole numbers are. My strategy here, I'm going to look at those people who can sit at each table, so 6 and 10. And I want to kind of find the least common multiple of those 2 numbers, 6 and 10. The common multiple of 6 and 10 is 30. So kind of for every 30 people, I can switch out the number of small and large tables I have. Because I would need, to seat 30 people, I would need 5 small tables, or I would need 3 large tables. So for every 5 small tables, I can replace that with 1, 2, 3 large tables. So there's a point here at 5 and 15. So there's a point at 5 and 15. And I can continue that pattern. I would have another example at 10 and 12. Again, I'm going up by 5 in my small tables and down by 3 with my large tables. I could have another point at 15 and 9, at 20 and 6, at 25 and 3, or at 30 and 0, which we already have written up here. So those are all possible solutions in the context of the problem. Again, you can either pull those off the graph if you've graphed it very carefully, or you can kind of use the least common multiple to help you find those other data points. And of course, you can check them by going back and plugging them into the original equation. So if I have x equals 5 and y equals 15, I can plug them into the original equation. 6 times 5 plus 10 times 15 equals 180. And sure enough, 30 plus 150 is 180. So that answer does check out. One last thing to note here. this graph should technically not be drawn as a straight line. It should be drawn as discrete data points because you can't have half of a table. You can only have whole numbers of tables. And so technically this graph should be drawn as these individual data points that I've listed here. However, it is often more convenient to graph a complete line segment instead of discrete points, just so that you can see where the line goes, and then you can find the data points from the line. Just make sure that any solutions you give are realistic solutions given the story problem. In this example, the number of tables always has to be a whole number. I hope this helped.